Alright, hello boys and girls. So today we will be looking at the axiomatic approach to probability, which is one of the most modern approaches that deals with the subject of probability. And previously we looked at the frequentist and the classical approach to that, and we saw the limitations as well. Now, what are the highlights of this framework? Well, this framework is, again, as I said, one of the most modern frameworks that deals with probability in a very mathematically sound manner. And by axiomatic, it means that it will have a set of axioms which will be rules governing a system, and based on these rules, other inferences and logical conclusions will be made. So any theorems, any lemmas, all of them will be derived from particular axioms that we will define later on. And this approach was developed by someone called Kolmogorov. He was a Russian mathematician during the Soviet Union, and this approach that he used uses axioms. And the highlight of this is that it does not use any concrete numbers per se. So if we look at the frequentist approach, you have the probability of A as NA, that is the number of trials in which A occurred, over N, the total number of trials. And as n tends to infinity, this probability of A becomes more and more accurate. And this thing, if you look at it, it deals with numbers. So any probability that we are having, it is being assigned a number based on the experiments that have been conducted. Now over here, this is a totally theoretical framework. It does not deal with concrete numbers, and any numbers that you assign are totally yours. The probabilities, the numbers that you assign are totally yours. And what this does tell us is how we can manipulate the system. Like, given some probabilities, how we can find out some other probability based on those. That's what it tells us. It gives us a framework to construct probability of events from the probability of other events that we may know, and how we assign the basic probabilities to construct the other events is totally up to us, and it must follow certain rules. And that's why it's the axiomatic approach. By itself, it's very theoretical. It won't have much real life application, but using some assumptions that assign those concrete numbers to certain events, that's when it has some real life use. So the next thing is something called a probability space. Before we get into the axioms, we need to define what this probability space is. Now, don't be confused by the name. It is actually a very simple thing. A probability space is any triplet omega fp, where omega is the sample space. So it contains all of the possible outcomes. So a trial, if you conduct a trial, you will observe an outcome, and omega is the set of all possible outcomes. Now f is an event. F is a collection of events, actually. And by collection of events, I mean a collection of subsets of this omega, that is the sample space. And as I'll elucidate later on, this f only contains a class of subsets of omega. Like in most cases, it will contain all of the subsets, but in certain cases, which I'll tell you later on, it will only contain a particular class of subsets, not all of them. But for all intents and purposes, please consider f to have all the subsets of omega for now. Now p is called a probability measure. Now p is basically a function that takes in an event from f and assigns a real number to it. Now the real number is called the probability of that event, and so you have omega fp, that's a probability space for any experiment. So given any experiment, you have to design the probability space, that is the omega, that's the sample space, the collection of events that are possible, and the probability measure for the events. And now the probability measure must satisfy these three axioms, that is for any event A. So this notation means any event A, the probability of A must be greater than or equal to 0. Yeah, sounds legit. I don't think probability should be negative anyways. So this is okay, simple stuff. The probability of the sample space, that is the certain event, that has to be 1. Okay, that is also something we have been that is also something we have seen so far, that's working. The third one, if A, B are 2 events and they're mutually exclusive. So by mutually exclusive, I mean A and B, those events don't have any common elements at all. So that's why it's A intersection B is phi. Phi is the null set, no common intersection. And in the case where A and B are mutually exclusive, the probability of A union B, and A union B is the event where either A occurs or B occurs or both of them occur. So the probability of that is the sum of the individual probability of A and B. Fair enough? Simple axioms. The first two make sense. The third is also okay. I mean, if you think of events as 2 blobs like this is A, this is B, and this is the in-between region. So what this is saying is that if A and B are disjoint, then the probability of this or both is basically the sum of the probability of A and B. Simple stuff. Okay, moving on. Some things to know about a trial in the axiomatic definition. So just like the classical definition of probability, the sample space contains the certain event. The sample space itself is the certain event. So by certain event, I mean since omega contains all of the outcomes, and if you consider omega as an event, then that event occurs in every trial, because one of the outcomes from omega will surely happen. So omega is the set of all possible outcomes, right? So one of those outcomes will happen in every trial. So that's why this is the certain event, and that carries over from the classical definition as well. Now F is the set of all possible events, and again it contains all the subsets of omega. For now, I'll explain when it does not contain all the subsets of omega. And probability measure, it's a function of the event space to the real line. It's a measure over F. And now omega occurs in every trial. Phi does not occur in any trial. It's the empty null event. And one thing is that this null event is not unique. There are many null events. So when I say null event, for all intents and purposes, it does not occur at all. And the null event is not unique. There are many null events. I'll get to where this comes from. Next is A union B. I already told you what it means. A intersection B. A and B both must occur. So now what is this? A subset of B. So this A subset of B means that if A occurs, then B must occur as well, because all the elements of A are contained within B. That's what this symbol means. So if I say that A is a subset of B, A is basically contained within B. And so if A has occurred, then obviously B has occurred as well. And what is A bar now? A bar is the event that A doesn't happen. So if A doesn't happen, all the elements that fall outside A within the sample space fall into A bar. So now let's dive into the properties. As I've said, till now I have only provided you the axioms. Now whatever you deduce from this is all up to you, but these axioms must be followed by the probability measure P. And few things we can deduce from that is that the probability of the null set is 0. So consider any event A. So A intersection phi is phi. The intersection of any set with nothing is basically nothing. And because of that, phi is a mutually exclusive event with pretty much everything. Phi and A, they are mutually exclusive, and the union of those two things is A itself, because any non-null any event, if you do a union with nothing, then nothing is added. So that's why the union will be the event A itself, and using the third axiom you can add the probabilities. So the union of A and phi, which is A, can be written as the sum of the individual probabilities, and using this equation over here you can cancel P of A from both sides, because of which the P of phi is 0. Now the next property that will be very useful is that the probability of A and probability of A bar summed together is 1. Again, A and A bar are obviously mutually exclusive, because A bar is that event where A doesn't occur. So all the elements outside A, they fall into A bar. So obviously they are mutually exclusive, and the union is the whole sample space by definition. So because of that, you can use this axiom 3 to say that P of omega is P of A plus P of A bar, and P of omega is 1 by the second axiom. And from here, this is where, now in the axioms it's not mentioned that the probability of A has to be less than 1. It just said it has to be greater than 0. But because of this, any event A will have a probability of which is less than 1. Why? Because P of A and P of A bar both will be greater than 0. They sum up to 1. So clearly both of them have to be less than or equal to 1. So that's why this thing comes into the picture. Now this property can be explained via this diagram, and to explain that, the probability of A union B. Now I haven't said anything about A and B being mutually exclusive over here. So this is the general case. If you take the A union B event, it is basically the sum minus something, minus the overlap region. Where does that come from? So A union B. So before I explain how to solve this, solving any sort of proofs, like proving any sort of theorems like this, first look at A union B and try to decompose it into two mutually exclusive events, as a union of two mutually exclusive events. Try to do that. So in our case, this whole thing is A union B, and if I want to decompose it as mutually exclusive events, I have A and I have this part. So what is this part? It's basically anything that falls outside A and within B. That can be written as A bar B. So A bar intersection B, anything that falls outside A and is within B. Now the union of A and this A bar B thing, that becomes A union B. And so because of that, we can write P of A union B as P of A plus P of AB, A bar B. Now similarly, B that is over here, that can be written as A bar B union the overlap region, that is AB. And similarly, I can write the probability of B as a sum of those two things, since they are mutually exclusive. And so from there, I can actually get this P of A bar B term in the terms of P of B and P of AB. And if I substitute that, I'll get the result. So for now, I'll stop here. I'll continue with the axiomatic approach, its good points, in the next one. Thank you.